Okay, good morning students. As you know, my name is Subodh Pandey and you are floating with me in the world of physics. We are going through a chapter and the chapter name is wave optics. In that chapter we have gone through a theory of very famous scientist, and the great scientist was Huygens. And he told us that light is nothing but a wave. Okay, so as we can say that the mechanical wave propagates in any medium, in the same way the light waves also propagates in any medium or travels through any medium, and the medium is taken as ether. So these all things we have already covered in the previous lectures. Okay, now in this topic, in this we can say that in the subtopic of the chapter, and the topic is reflection of light. And the reflection of light we have to gone through by using Huygens principle. So firstly we will start the laws of reflection of light. It is necessary that we have to recall the Huygens principle. So there are some basic points of the Huygens principle. What are those points? That we can simply say that if we have, let's suppose this is your pond, okay, like this way, and in that pond you throw a pebble, okay, so from this point the waves originates and progress in this pattern, you can see, okay, like this way. Your fluid waves, which are mechanical waves, travels from the point P, which is the origin of the waves, to the along side of the pond. It means we can simply say that if we talk about a point, let's suppose that be the point P1, and this is point P2, let be point P3, let be point P4. It means these points are the points of the medium, and as the wave propagates from the source and reaches to point P1, then the point P1 also behave like a same source as P. Okay, it means we can simply say that P1 behave like a new source. So this is the basic theory what Huygens told us, and on the behalf of that theory we are going to start our next topic, and the topic is reflection of light. So basic, as we know that reflection means let's suppose we have we can simply say that we have a what we have a this one, okay, so we have a surface like this way, okay, and this surface is polished. So let be this is your polished surface, okay, and now you have to take your incident rays. So let be these are your incident rays, this is your first ray, and let be this be your second ray, like this way, okay. So these two are the rays, we can simply say that, and these rays are parallel rays and are incidenting on your polished surface, let be your mirror or plane mirror, okay. So this is your plane mirror on which the parallel rays, or we can see the incident rays are falling, okay. Now as we have discussed earlier that in the laws of reflection the light bounces back in the same medium, Okay, so if we take the same concept here, then we have a normal like this way. You can simply say that this be your normal, okay, and this be your normal like this way, okay. And now we have to draw the reflected ray, so we can take this is a reflected ray, and this is also your reflected ray. So I hope that up to here each and everything is clear to all of you. So these two rays are your reflected rays, okay. So we have incident ray, we have a mirror or polished surface, and we have a reflected ray, or the rays which are bouncing back in the same medium. We also have some definite angles. This is your incident angle I, okay, and this be your angle of reflection R. So in the same pattern you can say that this will be angle of incidence I, and this will be the angle of incidence R. And why the angles I and R are same for the ray 1 as well as for ray 2? Because both are rays are parallel, and both are incident on the same mirror or same polished surface, okay. So this thing we have gone through in the previous we can say previous chapter, and your previous chapter was ray optics. So this all things we know very well, that what is the reflection, and I hope that it is clear now. Now the same concept, the same phenomenon we have to derive, we have to prove by using the Huygens principle. So basic logic, what we should do. So if we talk about the Huygens, then Huygens told us that we have a source, let be S, and a surface which is enclosing that source, let be sigma. And if a pulse is trying to reaches up to a point, any arbitrary point A, then it must be passed through the surface, that is sigma. And the point on that surface will also behave like a new source, okay. And from that new source, in every direction the new wavelets will emerges out like this way, okay. So this is your, we can say that it is primary source, and this be your secondary source. So in Huygens principle, basically we have to assume the two sources. One will be acted as your primary source, whereas your secondary source acted as the secondary source will be your new source, or we can say the new source of the disturbance, okay. So the concept of the Huygens, or we can say the theory of the Huygens, we have to apply in the law of reflection. So for that, what should we do? So firstly we have to take some, we can simply say that we have to take some primary sources there, some secondary sources will be there. So these are the basic criteria we have to follow. Now question is how we take primary source, primary source. This is your first question, and this question is obvious. Second is how we take secondary source. So in that condition we can simply assume that primary source can be represented by primary wave front, okay, and secondary source can be represented by secondary wave front. So we are in need of to understand what is the wavefront. So as in case of huygens, you have seen that we have a source like this way. Okay, we have a surface that will be your small sigma. Each and every point on that small sigma will be new source of light. These are the we can say the negative disturbance. After that we have positive disturbances like this way. So these things is very clear. Okay, and you have to draw a new wavefront like this way. Okay, or we can simply say that a tangent on the maximum disturbance, that is your capital sigma. So these points are the points of the secondary wave fronts. So this is your secondary wave front. Okay, this is your primary wave front. Okay, and this is your source, and the wave is emerging out in the all possible directions. So this is the basic concept to draw the primary wavefront and the secondary wavefront. It means you have to take your source. After that, after a finite distance, you have to take your first surface as a primary wavefront, and after some time interval, you have to choose another surface that is behave like a secondary wavefront. So this concept we will apply in the diagram of the ray optics. So let's get started. Firstly, what we have to do, we have to draw a diagram. So for that we will take like this way. So let be, this is your polished surface simply. Okay, and this be your polish. After that the incident rays, as you know, we have incident rays. So these are the sorry, so these are the incident rays. You can simply see here both rays are parallel to each other. Now what, as we know that if the source is here, or the source is sun, which is at infinity, that's why the rays are parallel. Okay, and we know that if the rays are parallel, then the wavefront will also be parallel. Okay, so for example, if we take a source like this way, this is source, and the light waves are spreading out. Okay, like this way, and when we draw a wavefront, then the wavefront will be spherical in shape like this way. But if we take a source which is at infinity, in that case the rays will be parallel, and in that case a plane wavefront will be there like this way. Okay, so the second case is applicable in this diagram. So the rays are parallel, so we have to draw a planar wavefront. So these rays are the incident rays, as I have already told you. It means whatever wavefront we will draw on the incident rays, that will behave like the primary wavefront. For that we take 2 points, let point A, let point B here. Okay, and we draw a perpendicular from point A like this way. Okay, this is the perpendicular which is we can simply say that which is started from point A and on ray 2. This be your ray 2 and this be your ray 1. Okay, so the A point is the starting point, and we can take here, let be point P. Okay, and P is the final point, and this be AP. AP is your primary wave front. So I hope and I believe that up to here each and everything is clear to all of you. Okay, now what? As I have told you that the each and every point on the primary wavefront will behave like the new source of light. It means we can simply take here that we can assume several points on this primary wavefront. Let be this point and here another point, this be a point, this be a point, this be a point. So there are several points which are behave like the new source of light. It means we can simply say that the light will move like this way, light wave will be move like this way, okay, and from this source light will move like this way, and from this source light, okay. So means from each and every point light will emerges out in the same pattern as is from the source. Okay, so what we see that each and every rays finally comes and reaches to the polished surface. This is your polished surface. So each and every ray which is coming from the new sources which are on the primary wavefront finally reaches to the polished surface. And after that what will happen? So firstly we will rough it. Okay, and as it reaches, then we know that it will bounce. So if the bouncing take place, then the bouncing will be like this way. Suppose the light rays, this will be bounced like this way, okay, and the light, the second ray will bounce like this way. So these two rays are also parallel to each other, okay. Now what? We have to draw your secondary wave front. So for that, what concept we will take here? So for that we will as in case of primary wavefront, we started a perpendicular from point A, okay, and the perpendicular is drawn on rays 2. In the same pattern, if we consider point B and draw a perpendicular, okay, so let be the perpendicular is like this way. This be your perpendicular, okay, and that point let be considered as Q, okay. So the every point which is on this wavefront, or we can say the QB. So QB is your secondary wave front. Now question is this, that what is the relation between the primary wavefront and the secondary wavefront? So the question is quite easy, that we can consider that whatever time is taken for wave 1 to reach to point A, let be the time is t, okay, the same time is taken by wave 2 to reach from source to point P, that time will be also t. It means the ray 1 is at point A and the ray 2 will at point B after time t, okay. It means the situation is this, that at point A and point B and point P, these 2 points we are getting after the same time, okay. Now if we see about the point Q and B, it means whatever the ray 2 takes time to move from point P to B, the same time, let's suppose the time t dash, okay, the same time is taken by the wave 1 which reaches from point A to Q. So this time is also be t dash. So this is the unique feature. It means for ray 1 we can simply say that from source to point A and for ray 2 from source to point P, the time is t, means equal. Okay. In the same way, for ray 1 to reach from point A to Q, and for point ray 2, the ray from point P to B. Okay, so the time is t dash, means the time will be same, and this will time t, and we get wavefront, that is your primary wavefront. It means after time t we get primary wavefront, and after time t dash we get secondary wavefronts. So that's why we have told you that after time t, so this be your time t, and after time t you have to consider such points, and on that points when we draw an envelope, then the envelope will behave like a wavefront, like this way. Okay, so this is your wavefront. So this is the calculation of the time, nothing else. So after time t we get a primary wavefront, and after time t dash we get the secondary wavefront, and each and every point on the primary wavefront will behave like the secondary wavelet. Okay, and each and every point on the secondary wavefront will behave like a tertiary wavelets. So this pattern is continuously goes on. So I hope that up to here each and everything is clear to all of you. Now what? Firstly we will rough it, and then we will start the things what we have discussed here, that we have to prove that the laws of reflection, and laws of reflection means the angle I must be equal to angle R. So where is the angle I, where is the angle R? For that we have to draw a normal. So we will draw a normal at point A and at point B. So let this be your normal, which is at point A, and this be your normal at point B. So you know that normal means basically the angle which represents 90 degree. Okay, this is your angle of incidence I, and this is your angle of reflection R. So that one is your angle I, this is your angle R. Okay, so according to sine, we can say according to the laws of reflection, the angle I must be equal to angle R. So this thing we have to prove. Now the question, how we prove it? So for that we take two triangle here. First is your triangle, you can see in the diagram, that is your triangle PAB, and second triangle is your triangle QAB. Okay, so if we just have a look on these two triangles, then you can easily see that the angle P, and that is equal to angle Q, and both are 90s, because we have drawn a perpendicular. And why we draw the perpendicular? We draw the perpendicular to construct the wavefront. So I hope that this point is clear. Now if we say that the PB, and that is equal to AQ. So PB, that is equal to AQ, because both are the length, and length is speed into time. Because we know that in the same medium the speed remains same. So here V is same, and T is taken as T dash in both cases. So V T dash and that are same. It means PB, that must be equal to AQ. And AB is your common side in both triangle. So this is your common side. So this is your side angle side. So this is the property. Side angle side means the two triangles are congruent. So if two triangles are congruent, it means we can simply say that the third angle must be equal. And if the third angle must be equal, it means we can simply say that the angle that is your PAB, okay, and that must be equal to angle, and that is your, we can simply say that QBA. Now interesting thing is this, that the angle QBA is equal to R, and angle PAB equal to angle I. It means simply we have that the angle I equal angle R. So this is the law of reflection. It means angle I must be equal to angle R. And finally we have proved it. So by using Huygen's principle, you can also derive the law of reflection as I have derived here. You can also derive the law of refraction. So how we can derive the law of refraction? By using Huygen's principle. So let's get started. Once again, as you can see in the picture, these are the two rays. Let me draw our diagram by ourselves. So firstly I will delete this diagram, and then we will see that what we can do. So this diagram will be deleted, and we will draw a new or fresh diagram for you, so that we can better understand what we are trying to say. So this is your, basically we can say that this is your interface. Interface means I have already told you that a surface which differentiate the two different medias. Okay, and after that as you know that we have two light waves. So this is your first light wave, and then you have second light wave like this way, and both rays are parallel to each other. As we talk about the laws of refraction, then we know very well that according to Snell's law, we have that the sine of angle of incidence over sine of angle of refraction must be equal to constant, and that constant is the refractive index. And refractive index nothing but the ratio of the speed in two different media. So this thing I have already told you in the previous chapter, that this is your refraction. It means we have to prove the refraction. So what should we do? We have to once again start with Huygen's principle. So let's suppose this be your source S, which is at infinity. Rays are parallel. We have take point A and we have to choose point B. Okay, and then we draw a perpendicular from point A on the wave 2. So this will be your first wave, this will be your second wave, and this will be your primary wave front. So that will be P. So here your AP is primary wave front. So this thing is quite similar as I have done in the previous derivation, that is law of reflection. Now as we know that now in this case the light will move from one medium to another. It means we can simply draw the diagram like this way. So the ray will be bent like this way, okay, and the second ray will also be bent like this way, okay. Now what, as we have done before, that from the second point we can simply say that from point B we have to draw, what we have to do, we have to draw a perpendicular like this way. Okay, so this point BQ and your BQ, that will be your secondary wave front. And as I have told you that the time to reach from source to point A is taken as t, and the same time t is taken by the ray 2 from source to point P. That's why this is your primary wavefront. Okay, and this time be taken as t dash, this time will be taken as t dash. It means the ray 1, or we can say the wave 1, will move from point A to Q in time t dash. At the same time t dash, the ray 2 will move from P to B. As you can see that we have to take the ratio of the two angles I and R. So for that we have to draw the angles I and angle R. So let's draw it. So that for that we have to draw a normal like this way at point A and at point B. So this will be your normal. Okay, and this be your angle I, and this be your angle R. Okay, now if this is I, then this will be I also, and if this is all R, then this will be R also. So in this case we will again take the two triangles. First is your PAB, and second one is your triangle QAB. It means the triangles are quite similar as in case of the law of reflection. But at that time we have to prove the two angles equal, and for that we made the two triangles congruent. But here we have to calculate the ratio of the two angles in terms of sine. So from first triangle we calculate sine I. So sine I is nothing but perpendicular, that is your PB upon hypotenuse, that is the longest side, as you all know. And from the second triangle we can easily calculate the value of sine R. So sine R, that will be again perpendicular, that is your AQ, and that is divided by the longest side, that is your AB. And we have to find out the ratio sine I and sine R. So let be this be equation first and this be equation number second. Now what we have to do, we have to divide equation first with second. Then what will we get? We get sine I upon sine R. So this will be sine I upon sine R, and sine I, that is PB upon AB. So it will be PB upon AB, and that will be divided by sine R. So sine R is AQ upon AB. So AQ upon AB. So AB and AB cancel out, and we have simply that it can be written as what we can written. We can write that that will be equal to AQ over PP. Okay, so AQ over PB. So where is AQ? AQ is this one, AQ, and this one is PB. Okay, so I hope that it is clear now. Let's get once we have to check that whether it is correct or incorrect. So it will be AB, and that will be AB upon AQ. So this with this cancel, so PB. Okay, so this is the little bit we can say that incorrect. So we have to write PB upon AQ. So this is we can say that that will be PB upon AQ, and this will be sine I upon sine R. Now what? PB. What is PB? As you can see in the picture that PB is the distance which is traveled by the wave 2 in medium 1 in time t1, t dash. So if the speed is taken as v1, so it will be v1 t dash, and aq is the distance which is taken by the wave 1 in medium 2 in the same time t dash. So it can be written as v2 t dash, and this will be sine over sine r. So t dash to t dash cancel out, and we have a result that sine I over sine r, and that is equal v1 over v2. And we know that v1 over v2, that is nothing but eta, or the refractive index of the medium, and this is your Snell's law. So I hope and I believe that law of reflection and law of refraction is now clear on the behalf of Huygens principle. So in that derivation, you have to focus on the construction of the primary wavefront and the secondary wavefront. How will you construct the primary wavefront and how will you construct the secondary wavefront? The process is quite easy. You have to choose your source, then after some time you have to draw a surface, then after some time then you have to draw again a surface. This is your primary surface, and the envelope on the primary surface will be primary wavefront. After some time, let be this time t, then time t dash, we have to take capital sigma, and an envelope on it will be have like your secondary wavefront. So this is depends upon your mindset that how will you consider the surfaces, in which direction you have to choose the wavefronts. So as in this case, we can simply say that when we talk about the reflection, then at that time we have considered the wavefront which are in the same medium, as well as one is on the incident ray, whereas on second is on the reflected ray. In the second pattern, when we draw the diagram for refraction, then the primary wavefront will be on incident ray, and the secondary wavefront is on the refracted wave. So I hope and I believe that each and everything is clear to all of you. So thanks for listening, thanks for watching, and just keep in touch with me, and I hope that this journey will be quite interesting, and I hope enjoyable also. So best of luck to all of you. Thank you.